Welcome to this introduction to Combustion Studio, a comprehensive desktop application designed for engineers, researchers, and students working in combustion, energy systems, fire safety, and chemical kinetics. Combustion Studio is organized into a three-panel interface designed for clarity, efficiency, and technical transparency. 1. Left sidebar module navigation serves the primary navigation panel. It lists all computational modules and analysis tools in a structured hierarchy. 2. Center panel main calculation window. The middle region of the interface is the core workspace where calculations, simulations, and visualizations occur. 3. Right sidebar methodology and theory. The right sidebar provides contextual scientific documentation, synchronized with the active module. The left sidebar serves as the primary navigation panel. It lists all computational modules and analysis tools in a structured hierarchy. Users can quickly switch between different domains. List of tabs are working directory, volume, ASED calculator, mass-based calculator, AFR versus equivalence, ratio plot, adiabatic flame temperature plot, flame speed plot, fuel energy and emissions, fuel comparison, combustion products, fuel blending calculator, Cantera, equilibrium combustion, Cantera, incomplete combustion analysis, Cantera, premixed combustion regime analysis, Cantera, PEDA regime plot, ignition delay calculation, Cantera, ignition delay plot, flammability and stability limits, flame and stability simulation, Cantera, premix burner risk map, Cantera, pollutants, fire load and hazard assessment, ventilation effect, toxicity estimation, reduced order model, ROM, Cantera, ROM ignition delay plot, ROM radicals plot, pyrolysis gas combustion stoichiometry, material properties explanation, learning output, center panel main calculation window. The middle region of the interface is the core workspace where calculations, simulations, and visualizations occur, depending on the selected module. This panel displays input fields, parameter configurations, tabs for setup, simulation, and results, real-time plots, tabular outputs, graphical representations, detailed calculation results. The right sidebar provides contextual scientific documentation synchronized with the active module. Inner tabs are methodology, explains the computational approach, numerical model, assumptions, and equations implemented in the selected tool. Theory provides the thermodynamic, chemical, and physical principles behind the method, including reaction mechanisms, combustion theory, and reference formulas. AI support. Results are reviewed and suggestions are given. Combustion Studio generates a structured prompt so users don't need to know anything about prompt engineering. Inputs, results, calculations performed and user goal are injected to AI model. Why this is powerful for users without prompt knowledge. No manual prompt writing. Users just run the case and see results. The prompt builder automatically wraps this into a structured, educational request consistent format. Every tab in Combustion Studio produces prompts with the same sections: purpose, inputs, results, calculations, user goal. This consistency makes AI responses predictable and reliable. Domain-specific guidance. AI model responds as a combustion educator. Educational clarity. The AI explains physical meaning, trends, and next steps, exactly what students and researchers need. Combustion Studio is designed to help you work efficiently, save your progress, and organize multiple combustion analysis cases. The project session management system ensures that all your inputs, selections, and results can be stored, reopened, and shared whenever needed. Combustion Studio brings engineering productivity to the next level by integrating smart QR codes directly into your reports and case files. Asterisk. Each QR code embeds your full calculation parameters, fuel properties, operating conditions, modeling choices, and results, so collaborators can instantly reopen your scenario on any device without manually entering data. This enables faster peer review, eliminates input mistakes, and allows seamless sharing between students, engineers, and supervisors. Whether you're documenting experiments, presenting results, or transferring cases between desktop and mobile devices, QR-enabled workflows make Combustion Studio feel smarter. The use of QR codes in Combustion Studio accelerates digitalization by turning every calculation, report, and case file into a portable, machine-readable data object, instead of relying on static PDFs, printed reports, or manual data entry. QR codes allow users to instantly transfer complete combustion scenarios between devices, platforms, and people. This reduces paperwork, eliminates transcription errors, and enables seamless integration with digital workflows such as mobile review, cloud archiving, automated documentation, and real-time collaboration. By embedding structured data directly into a scannable code, Combustion Studio transforms traditional combustion engineering processes, often dominated by spreadsheets and handwritten notes, into fast, connected, and fully digital interactions. It includes several key modules designed to perform both theoretical and numerical combustion analyses. Volume-based calculator, mass-based calculator, AFR versus equivalence ratio plot, adiabatic flame temperature plot, flame speed plot, fuel energy and emissions, fuel comparison, combustion products. All these modules share a set of common input parameters, such as fuel type, fuel and air mass or volume equivalence ratio or air-fuel ratio. AFR. The volume-based calculator tab. This tab allows users to perform combustion calculations based on the volumetric inputs of fuel and air. It is typically the first step in the analysis, where the user defines the mixture composition and initial combustion setup. The software then automatically computes the corresponding air-fuel ratios and other combustion parameters. User inputs fuel type, methane calculation mode, fuel volume plus excess air fuel flow, 15.00 Newton meters cubed, H excess air, 20.0% temperature, 25.0 degrees Celsius pressure, 1.0 atmospheres. Calculated results. Fuel density computed 0.6556 kilograms per cubic meter. Air density computed 1.1841 kilograms per cubic meter. Fuel mass flow 0.002732 kilograms per second. Air mass flow 0.056383 kilograms per second. AFR. Air, fuel, 20.64. 1 equivalence ratio, 0.83 lambda, 1.20 feedback. Lean mixture, risk of high NOx emissions. The mass-based calculator tab. The mass-based combustion calculator focuses on analyzing the combustion process using fuel and oxidizer masses directly. This approach is particularly useful in experimental or engineering applications where the mass of fuel and air are known or measured directly. It is ideal for comparing combustion efficiency and emission characteristics. This tab shows the AFR versus equivalence ratio plot. The plot provides a clear visual relationship between air-fuel ratio and equivalence ratio for selected fuels. The air-fuel ratio, AFR, and the equivalence ratio are two of the most fundamental parameters used to describe combustion mixtures. They define whether a mixture is lean, stoichiometric, or rich, and strongly influence flame temperature, emissions, and combustion efficiency. This tab shows adiabatic flame temperature plot. This module computes and visualizes the adiabatic Flame temperature as a function of the equivalence ratio. Phi. For the selected fuel and oxidizer, this analysis is crucial in understanding combustion processes and optimizing efficiency. The results plot TAD, adiabatic flame temperature, versus I, the equivalence ratio, which quantifies the richness or leanness of the fuel mixture. An equivalence ratio of 1 indicates a stoichiometric mixture, while values below and above 1 represent lean and rich mixtures, respectively. This tab shows the flame speed plot in this simulation. We calculated the laminar flame speed of hydrogen at an equivalence ratio of 1.000, which is equal to stoichiometric conditions. The laminar flame speed indicates how fast a flame front propagates in a static environment, without turbulence or other factors influencing it. In this case, the calculated laminar flame speed for hydrogen is 1.70 meters per second. Plotting the flame speed versus equivalence ratio, phi, would reveal that the flame speed increases as we approach stoichiometric conditions, around phi equals 1.0, then decreases as the equivalence ratio exceeds 1.0. Lean mixtures, or falls below 1.0. Rich mixtures. This trend suggests that, for hydrogen combustion, the optimal fuel-air mixture occurs near stoichiometric conditions to achieve the highest flame propagation speed. Fuel energy and emissions. This module calculates the energy output and major combustion products using previously defined input parameters: fuel type, calculation type, fuel mass, and air mass. In this combustion analysis, we've evaluated the energy content and environmental emissions of hydrogen fuel using the provided masses of hydrogen and air. Here's a breakdown of the results. Lower heating value, LHV, and higher heating value, HHV. LHV represents the amount of heat released during combustion, accounting for the energy loss due to water vapor formation within the fuel itself. HHV, on the other hand, accounts for the water vapor formed during combustion as if it were condensed back into liquid and recovered as useful energy. In this case, both LHV and HHV are equal at 0.28 megajoule per kilogram since hydrogen doesn't contain any water content initially. Fuel Comparison tab. This tab uses standard combustion data to compute and visualize the comparative performance of hydrogen, methane, and propane. Each fuel's LHV, HHV, CO2 emissions, and enthalpy of combustion, delta H, are stored in predefined reference tables derived from thermochemical data. The graphical output makes it easy to compare fuels in terms of both energy efficiency and carbon footprint, reinforcing key thermodynamic and environmental principles of combustion. Combustion products. This module automatically computes the composition of combustion products based on previously defined inputs such as fuel type, calculation type, fuel mass, and air mass. No additional user input is required in this tab. AI support. As a combustion educator, let's dive into the results of your hydrogen combustion experiment. Equivalence ratio and excess_air deficiency. The equivalence ratio phi is a measure that defines the richness or leanness of the air-fuel mixture in comparison to the stoichiometric optimal combustion condition. In this case, your equivalence ratio of 0.99 indicates that the fuel-air mixture has slightly more air than necessary for complete combustion. Stoichiometric ratio is typically around 1.0 for hydrogen. The excess air of 0.7% means that there is an additional 0.7% oxygen in the mixture compared to the optimal condition. Chemical equilibrium and simulation. Overview. The chemical equilibrium and simulation module of Combustion Studio brings advanced combustion science into an accessible, interactive environment. This section allows engineers, researchers, and students to explore fuel behavior under realistic reacting conditions using state-of-the-art chemical kinetics and equilibrium tools powered by Cantera. By combining equilibrium calculations, ignition delay prediction, combustion regime classification, and fuel blending simulation, this module provides a unified platform for analyzing both ideal and real combustion processes. Compute equilibrium combustion products and adiabatic flame temperature for any fuel. Analyze incomplete combustion, including CO formation and residual species. Examine premixed flame regimes, identifying laminar versus turbulent behavior. Visualize chemical timescales using PEDA, Pecklet-Damkohler regime plots. Predict ignition delay under varying temperature, pressure, and mixture conditions. Generate ignition delay plots directly from detailed chemical mechanisms. Blend multiple fuels and evaluate how mixture composition influences combustion performance. Whether the user is designing burners, studying pollutant formation, optimizing fuel mixtures, or learning combustion fundamentals, the Chemical Equilibrium and Simulation Suite delivers a comprehensive, scientifically accurate, and intuitive environment for advanced combustion analysis. Equilibrium combustion Cantera. This tab computes equilibrium combustion products and adiabatic flame temperature for any fuel. In this tab, the equilibrium state is determined using Cantera, a robust thermodynamic and chemical kinetics library. Cantera minimizes Gibbs free energy under constant pressure and enthalpy constraints to compute both the adiabatic flame temperature and the equilibrium product composition. User inputs: fuel type, hydrogen calculation mode, fuel mass plus air mass, fuel mass, G, 2.0 air mass, G, 68.7 initial temperature, K, 298.15 initial pressure, PA, 101,325.0 mechanism file. GRI 30. YAML calculated results: equilibrium adiabatic flame temperature, K, 2375.4 equivalence ratio, 0.99 lambda, 1.01 species mole fraction mass fraction N2 0.6457, 0.7438 H2O, 0.3232, 0.2394 H2, 0.0138, 0.00110, 0.0069, 0.0048 O2, 0.0054, 0.0071 number, 0.0027, 0.0033 H, 0.0017, 0.0001 O, 0.0006, 0.0004 total 1.0000, 1.0000. Incomplete combustion analysis. Cantera tab at Analyze incomplete combustion, including CO formation and residual species. In this analysis using Combustion Studio, we simulated an incomplete combustion scenario of methane under specific conditions. The purpose of such a simulation is to estimate unburned species and CO formation that can help us understand the performance of a combustion system and identify areas for improvement. Incomplete combustion analysis. Cantera tab at Analyze incomplete combustion, including CO formation and residual species. In this analysis using Combustion Studio, we simulated an incomplete combustion scenario of methane under specific conditions. The purpose of such a simulation is to estimate unburned species and CO formation that can help us understand the performance of a combustion system and identify areas for improvement. Premixed combustion regime analysis. Cantera premixed combustion refers to a process where fuel and oxidizer are mixed at the molecular level before ignition. The resulting flame structure depends strongly on the relative influence of chemical reaction rates and transport processes, convection and diffusion. In this analysis using Cantera, we have determined the flame stability regimes for a premixed combustion scenario. The Pakelet number, Pe, and Damkohler number, Da, are key non-dimensional parameters computed from the given inputs that help us understand the combustion regime. Furthermore, it is worth exploring numerical simulations using ANSYS Fluent to further investigate the effects of fuel type, flow properties, and reaction kinetics on flame stability and combustion regime boundaries. The recommended model for this analysis is a combination of FRC, flamelet reaction progress variable, and EDM, Edwards-Bilger diffusion model, which can capture the features of both thin reaction zones and distributed combustion regimes. PEDA regime plot. The Pakelet number, Pe, and Damkohler number, Da, are two fundamental dimensionless parameters that characterize the interplay between flow, mixing, and chemical reaction in combustion systems. The PEDA diagram helps identify the combustion regime. In turbulent flames, different combinations of Pe and Da determine whether the flame is smooth and laminar, wrinkled by turbulence, or fully distributed within the flow field.